Hello there, and welcome. I'm so glad you found your way here tonight. Perhaps you've had a long day, or maybe you're simply the kind of person who enjoys drifting off to sleep while learning about the quiet marvels that surround us. Either way, you're in the right place. Tonight, we're going to explore something you encounter every single day, something so common that you might not think twice about it. And yet, it performs a feat that seems almost magical when you really stop to consider it. We're going to talk about your refrigerator. Yes, that humming box in your kitchen. The one that keeps your milk cold, your vegetables crisp, and your ice cream frozen. But here's the thing that makes it truly remarkable. Your refrigerator doesn't actually make cold. That might sound strange at first, but it's true. Cold, as a concept, doesn't really exist as something you can create. What your refrigerator actually does is far more interesting. It extracts heat. It pulls warmth away from the inside and moves it to the outside. It's a heat pump working in reverse, a quiet mechanical marvel that works against the natural flow of energy. And it does this every single moment, day and night, without you ever having to think about it. Tonight, as you settle in and let your breathing slow, we're going to take a gentle journey through the inner workings of this everyday appliance. We'll explore how heat moves, why it wants to flow in certain directions, and how engineers have created systems that can persuade it to go somewhere it doesn't naturally want to go. We'll look at compressors that squeeze gases, coils that absorb and release heat, tiny tubes that create dramatic pressure drops, and foams that trap countless tiny bubbles of air. And we'll do all of this slowly, methodically, with plenty of time to let each concept settle in your mind like snow falling on a quiet winter evening. There's nothing you need to do right now except relax. Let your body sink into comfort. Let your mind wander through these ideas without effort. Because understanding how a refrigerator works isn't just about mechanics and thermodynamics. It's about appreciating the invisible dance of molecules, the patient flow of energy, and the elegant solutions that humans have discovered to keep our food fresh and our drinks cold. So take a deep breath, let it out slowly, and let's begin our exploration of how refrigerators extract heat to stay cold. Before we can understand how a refrigerator works, we need to understand something fundamental about heat itself. Heat is not a substance. It's not a thing you can hold or see. Heat is energy in motion. It's the vibration of molecules, the kinetic energy of atoms bouncing against one another. And this energy has a very strong preference for how it likes to move through the world. Heat always flows from warmer places to cooler places. Always. This isn't just a tendency or a general rule. It's one of the fundamental laws of thermodynamics, one of the bedrock principles that governs how energy behaves in our universe. If you place a hot cup of coffee on a table, the heat from that coffee doesn't stay put. It flows outward, spreading into the cooler air around it, radiating from the cup into the table beneath it, dispersing until everything reaches the same temperature. The coffee cools down, the room warms up ever so slightly, and equilibrium is eventually reached. This principle is so fundamental that it's called the Second Law of Thermodynamics. In its simplest form, it tells us that heat will not spontaneously flow from a cold object to a hot object. It just won't. Not on its own. Not without something forcing it to happen. If you put an ice cube on a warm countertop, The heat from the countertop flows into the ice cube, melting it. The ice cube doesn't somehow make the countertop colder by pulling cold out of itself. Cold isn't really a thing. Cold is simply the absence of heat. The ice cube melts because heat flows into it from the warmer surface around it. Now, here's where refrigerators become fascinating. A refrigerator needs to keep its inside cold, which means it needs to remove heat from the food and air inside the cabinet. But heat naturally wants to flow from warm to cold. So how do you make heat flow from something already cold, like the inside of your refrigerator, into something warmer, like your kitchen? The answer is, you can't do it spontaneously. You need to add energy to the system. You need to work against nature's preference. And that's exactly what a refrigerator does. Think of it like water flowing downhill. Water naturally flows from high places to low places because of gravity. If you want water to flow uphill, you need a pump. You need to add energy to push that water against gravity's pull. A refrigerator is similar. It's a heat pump. It uses energy, electrical energy from your wall outlet, to push heat from a cold place inside the refrigerator to a warmer place outside of it. It works against the natural direction of heat flow, and in doing so, it keeps your food cold. The amount of energy required to do this depends on several factors. How cold do you want the inside to be? How warm is the room around it? How well insulated is the refrigerator? How often do you open the door and let warm air rush in? All of these factors matter, but the basic principle remains the same. The refrigerator must continuously work to remove heat from inside and reject it to the outside. It never gets to rest. As long as it's plugged in and turned on, it's engaged in this endless battle against the second law of thermodynamics, moving heat in a direction it doesn't want to go. This might sound exhausting, and in a way, it is. A refrigerator uses more electricity than almost any other appliance in your home, precisely because it's always working. But modern refrigerators are remarkably efficient at this task. They've been refined over more than a century of engineering improvements. The compressors are quieter, more reliable. The insulation is better. The materials are more carefully chosen. And the result is a machine that can maintain a temperature differential of 30, 40, even 50 degrees or more between its inside and the room around it. And it can do this continuously, year after year, with nothing more than the electricity flowing through your walls. To understand how this magic happens, we need to look at the refrigeration cycle. This is the heart of how a refrigerator works, the elegant loop of processes that allows it to absorb heat on one end and release it on the other. The cycle involves a special fluid called a refrigerant that flows continuously through a closed system of pipes and components. This refrigerant changes state, from liquid to gas, and back again, over and over, and in doing so, it carries heat with it. It absorbs heat where you want cooling, and it releases heat where you can afford to add warmth. There are 4 main components in this cycle, and each one has a specific job to do. There's the compressor, which squeezes the refrigerant gas, raising its pressure and temperature. There's the condenser, which is a set of coils where the hot, high-pressure refrigerant releases its heat to the outside air. There's the expansion device, usually a tiny tube or valve, where the pressure drops dramatically, allowing the refrigerant to cool down. And there's the evaporator, another set of coils where the cold refrigerant absorbs heat from inside the refrigerator. These four components work together in a continuous loop, moving the refrigerant around and around, carrying heat with it from inside to outside, over and over again. Each of these components deserves its own careful exploration. We'll visit each one in turn, taking our time, letting the details settle in gently. We'll see how metal tubes are bent into coils, how gases compress and expand, how pressure drops create cold, and how heat radiates away into the air. We'll learn about the materials used, copper and aluminum and steel, chosen for their ability to conduct heat. We'll discover the physics of phase changes, how liquids evaporate into gases and gases condense back into liquids, and how these transformations involve enormous amounts of energy. But first, let's just appreciate the elegance of it all. Heat wants to flow from warm to cold. A refrigerator makes it flow from cold to warm, and it does this not by violating the laws of physics, but by using them cleverly, by adding energy at just the right points, by manipulating pressure and temperature and phase changes, all coordinated in a carefully designed cycle. It's like a dance, choreographed by engineers and performed by molecules, happening right now in your kitchen, keeping your food fresh while you sleep. At the heart of every refrigerator is a closed-loop system, a continuous pathway that the refrigerant travels through again and again. This loop is called the refrigeration cycle, sometimes known as the vapor compression cycle. It's called vapor compression because one of the key steps involves compressing a vapor, a refrigerant gas, to change its properties. But the full cycle involves much more than just compression. It involves 4 distinct stages, 4 transformations that the refrigerant undergoes as it travels through the system. Let's follow a single molecule of refrigerant as it makes this journey. Imagine it as a tiny traveler, moving through pipes and coils, changing form, absorbing energy here and releasing it there. Our journey begins at the compressor, but we could start anywhere in the loop since it's continuous. For now, though, let's start where the action begins, where energy is first added to the system. Our refrigerant molecule enters the compressor as a low-pressure gas. It's cool, maybe even slightly cold, and it's just finished its tour through the evaporator inside the refrigerator, where it absorbed heat from the food and air. Now it's returning to the compressor to begin a new cycle. The compressor's job is simple but crucial. Squeeze this gas. Compress it. Reduce its volume and increase its pressure. When you compress a gas, something interesting happens. The molecules get pushed closer together. They have less room to move around. And when molecules are forced closer together, especially when you do it quickly, they start bouncing off each other more vigorously. This creates heat. It's the same reason a bicycle pump gets warm when you're inflating a tire. You're compressing air, forcing the molecules together, and the compression generates heat. In a refrigerator, this effect is intentional and essential. The compressor takes in cool, low-pressure refrigerant gas and outputs hot, high-pressure refrigerant gas. How hot? Much hotter than the room around it. Depending on the refrigerant being used and the operating conditions, the refrigerant leaving the compressor could reach temperatures of 50 to 80 degrees Celsius, roughly 120 to 175 degrees Fahrenheit. This is important because, remember, heat flows from hot to cold. By making the refrigerant very hot, hotter than the kitchen air, we create a temperature difference that will allow heat to flow out of the refrigerant and into the room. This is the opposite of what we want inside the refrigerator, but it's exactly what we need at this stage of the cycle. Our hot, pressurized refrigerant molecule now travels through a discharge line, a sturdy copper tube, toward the condenser. The condenser is a series of coils, metal tubes bent into loops or zigzag patterns, designed to maximize surface area. These coils are usually found on the back of your refrigerator, or sometimes underneath it, behind a grill. You've probably felt the warmth radiating from the back of a refrigerator. That warmth is coming from the condenser coils. This is where the refrigerator is rejecting heat, pushing it out into your kitchen. As our refrigerant molecule flows through these condenser coils, it gives up its heat. The metal of the coils conducts the heat from the refrigerant to the outside surface, where it radiates into the surrounding air. Sometimes there's a small fan helping to move air across these coils, especially in more efficient models, but often it's just natural convection. The warm air rises, cooler air replaces it, and slowly, gradually, the refrigerant cools down. But here's the crucial part. The refrigerant isn't just cooling down, it's also changing state. As it loses heat while remaining at high pressure, it transitions from a gas back into a liquid. This is called condensation. It's the same process that creates dew on grass in the morning or makes water droplets form on the outside of a cold glass. When a gas cools enough, it condenses into a liquid. And when refrigerant condenses, it releases a lot of energy, because the phase change from gas to liquid involves giving up what's called latent heat. Latent heat is the energy required to change the state of a substance without changing its temperature. When water boils, it absorbs energy to change from liquid to steam, even though both the boiling water and the steam are at 100 degrees Celsius. That energy goes into breaking the bonds between molecules. Similarly, when steam condenses back into water, it releases that energy. In a refrigerator's condenser, when the refrigerant condenses from gas to liquid, it releases a substantial amount of heat. This is the heat that was absorbed from inside the refrigerator, plus the heat generated by the compression process. All of it flows out through the condenser coils into your kitchen. Now, our refrigerant molecule is a liquid. It's still under high pressure, but it's cooled down significantly. It's probably only slightly warmer than room temperature at this point. It flows along another section of copper tubing toward the next component in the cycle, the expansion device. The expansion device is surprisingly simple, often nothing more than a very thin, very long tube called a capillary tube. It might be just 1 or 2 millimeters in diameter on the inside and several meters long, coiled up to save space. The refrigerant enters this tiny tube under high pressure. The tube is so narrow that it creates a restriction, a bottleneck. And as the liquid refrigerant squeezes through this restriction, its pressure drops dramatically. This pressure drop is where the cooling really begins. When a liquid experiences a sudden drop in pressure, some of it flashes into vapor. Think of opening a bottle of soda. The liquid is under pressure inside the bottle. When you open the cap, the pressure drops, and you see bubbles form instantly. Some of the dissolved carbon dioxide comes out of solution as gas. Something similar happens with refrigerant. As it passes through the expansion device and the pressure plummets, some of the liquid refrigerant evaporates instantly. And evaporation requires energy. Where does that energy come from? From the refrigerant itself. So the refrigerant cools down. It becomes very cold, much colder than the inside of your refrigerator. Now, our refrigerant molecule, or the mixture of liquid and vapor that includes our molecule, enters the evaporator. The evaporator is another set of coils, similar to the condenser, but located inside the refrigerator or freezer compartment. These coils might be hidden behind a panel, or they might be visible as a frosted surface in older freezers. The refrigerant flowing through these coils is very cold, colder than the air and food around it. And remember, heat flows from warm to cold. So now, heat from inside the refrigerator flows into the cold refrigerant. As the refrigerant absorbs this heat, the liquid portion continues to evaporate, turning into gas. This evaporation process absorbs a lot of energy, again because of latent heat. When water evaporates from your skin, it cools you down because the phase change from liquid to gas requires energy, which is drawn from your warm skin. The same principle works in the evaporator. As refrigerant evaporates, it absorbs heat from the surrounding air and food. The inside of the refrigerator gets colder, and the refrigerant becomes a low-pressure gas. This low-pressure gas, now warmed slightly from absorbing heat but still cooler than room temperature, flows back to the compressor through the suction line, and the cycle begins again. Compression, condensation, expansion, evaporation. Over and over, continuously. As long as the refrigerator is running, this cycle never stops. The refrigerant loops through the system, carrying heat from inside to outside, maintaining that temperature difference that keeps your food fresh. It's a beautiful system in its elegant simplicity. 4 components working together in harmony. The compressor adds energy, raising pressure and temperature. The condenser removes heat, changing gas to liquid. The expansion device drops pressure, cooling the refrigerant, and the evaporator absorbs heat, changing liquid to gas. Each step flows naturally into the next, guided by the properties of the refrigerant and the laws of thermodynamics. The cycle runs efficiently when everything is balanced. The compressor must be powerful enough to maintain the pressure difference. The condenser must have enough surface area to reject all the heat. The expansion device must provide exactly the right restriction, and the evaporator must be able to absorb heat without frosting over too quickly. Engineers spend enormous amounts of time optimizing each component, choosing the right materials, calculating the perfect tube diameters, determining ideal refrigerant charges, all to create a system that runs smoothly, quietly, efficiently, keeping your food cold for years with minimal attention. If the refrigeration cycle were a living thing, the compressor would be its heart. It's the component that drives everything else, the source of motion and energy. Without the compressor, the refrigerant would just sit there, static, unable to move through the system. The compressor is what creates the pressure difference that allows the cycle to function. It's what pushes the refrigerant forward, loop after loop, day after day. Most refrigerators use what's called a hermetically sealed compressor. Hermetic means airtight, completely sealed. In this design, the compressor mechanism and the electric motor that drives it are enclosed together in a single steel housing, welded shut. You can't open it for repairs. If it fails, you replace the entire unit. This might sound inconvenient, but it has significant advantages. The sealed housing protects the internal components from dust, moisture, and contaminants. It prevents refrigerant from leaking out, and it simplifies manufacturing, making compressors more reliable and affordable. Inside this sealed housing is a motor, typically an electric motor that runs on the alternating current from your wall outlet. In most household refrigerators, this is a single-phase motor running at either 60 Hz in North America or 50 Hz in most other parts of the world. The motor's shaft connects directly to the compression mechanism. There are different types of compression mechanisms, but the most common in household refrigerators is the reciprocating design. A reciprocating compressor works much like an engine in a car, but in reverse. Instead of burning fuel to push pistons and create motion, it uses motion to push a piston and compress gas. The motor turns a crankshaft. The crankshaft converts the rotational motion into back-and-forth linear motion, just like the pistons in your car engine. This linear motion drives one or more pistons inside cylinders. Each cylinder has two valves, an intake valve and a discharge valve. These valves are often simple reed valves, thin metal flaps that open and close based on pressure differences. Here's how it works. As the piston moves down in its cylinder, it creates a vacuum, a region of lower pressure. This low pressure causes the intake valve to open. Low-pressure refrigerant gas from the evaporator flows in through the intake valve, filling the cylinder. Then the piston reverses direction and moves up. As it moves up, it compresses the gas, reducing its volume and increasing its pressure. The pressure builds until it's high enough to overcome the spring tension on the discharge valve, at which point the discharge valve opens and the hot, compressed gas flows out toward the condenser. This happens very rapidly. The piston might cycle up and down 30 to 60 times per second, depending on the motor speed and the compressor design. Each stroke compresses a small volume of gas. Over time, this continuous compression maintains the pressure difference throughout the system. It's a mechanical process, with moving metal parts sliding against each other, bearings rotating, valves opening and closing. And all of this happens inside that sealed steel housing, bathed in refrigerant and oil. Oil is essential in a compressor. The moving parts need lubrication to prevent friction and wear. Special refrigeration oils are used, chosen to be compatible with the refrigerant and to remain fluid even at the very cold temperatures found in the low-pressure side of the system. The oil circulates through the compressor, coating the surfaces of pistons and cylinders, ensuring smooth operation. A small amount of oil also circulates through the rest of the refrigeration system, carried along with the refrigerant, though most of it stays in the compressor where it's needed most. The compressor generates heat. Some of this heat comes from the compression process itself, as we discussed earlier. When you compress a gas, you do work on it, and that work becomes heat. But additional heat also comes from the inefficiencies of the motor and the friction in the moving parts. This heat must be dissipated. In most hermetic compressors, the housing is designed to radiate heat away into the surrounding air. Sometimes there are fins or plates welded to the housing to increase surface area. The cool, low-pressure refrigerant entering the compressor also helps to cool it from the inside. absorbing some of the heat before it even reaches the condenser. Different refrigerators use different types of compressors. While reciprocating compressors are most common, some use rotary compressors. A rotary compressor uses a rotating vane or roller inside an eccentrically mounted cylinder. As the roller rotates, it traps gas on one side and compresses it as the space decreases. Rotary compressors are often quieter than reciprocating ones because they have fewer moving parts that change direction abruptly. They're common in smaller refrigerators and in many air conditioning units. Then there are scroll compressors, which use two interleaved spiral-shaped scrolls. One scroll is fixed, and the other orbits around it without rotating. As the mobile scroll orbits, pockets of gas are formed at the outer edge, gradually compressed as they spiral inward toward the center, where the high-pressure gas is discharged. Scroll compressors are very efficient and very quiet, though they're more commonly found in larger commercial refrigeration systems and HVAC units than in household refrigerators. Regardless of the specific design, all these compressors share a common purpose: to take in low-pressure gas and output high-pressure gas. They do this continuously while the refrigerator is running. But here's something interesting. Most refrigerators don't run continuously. The compressor cycles on and off. When the temperature inside rises above the set point, a thermostat or electronic control signals the compressor to start. The compressor runs, removing heat, cooling the interior. Once the temperature drops to the desired level, the control signals the compressor to stop. The system rests until the temperature rises again. This cycling is normal and efficient. Running continuously would waste energy, because once the interior is cold enough, there's no need to remove more heat until warm air leaks in or warm food is added. The frequency of these cycles depends on many factors: the insulation quality, the ambient temperature, how often the door is opened, how much food is inside. In a well-insulated refrigerator in a cool room, the compressor might run only 20 to 30% of the time, though this can vary. In a hot kitchen with frequent door openings, it might run 50 to 70% of the time, or even more. Modern compressors are remarkably durable. They're designed to operate for tens of thousands of hours over 15 to 20 years or more. The bearings are precision-made. The clearances between pistons and cylinders are carefully controlled. The materials are chosen for their strength and resistance to wear. And because the system is hermetically sealed, there's no exposure to atmospheric moisture or oxygen, which reduces corrosion. You can often hear the compressor when it's running. There's a low hum, the sound of the electric motor. Sometimes you might hear a slight clicking or tapping, the sound of the valves opening and closing, though modern compressors are usually quiet enough that this is barely noticeable. When the compressor starts up, there might be a brief surge, a momentary louder sound as the motor overcomes the initial resistance, and when it shuts off, you might hear the system settling, the refrigerant pressure equalizing throughout the coils with a gentle hissing or gurgling. These sounds are all normal, part of the refrigerator's life. They're the sounds of the compressor doing its job, tirelessly compressing refrigerant, creating the pressure difference that allows the entire system to function. The compressor is working so you don't have to. It's laboring continuously, or at least intermittently, maintaining that careful balance between the cold interior and the warm exterior. keeping your food fresh, your drinks cold, your ice cream frozen. And it does this so reliably that you rarely think about it. But if you ever sit quietly and listen, you might hear it kick on, that familiar hum starting up, and you can appreciate the engineering that goes into this simple but essential device. After leaving the compressor, the hot, high-pressure refrigerant gas travels through the discharge line towards the condenser. This is where the magic of heat rejection happens. The condenser is essentially a long pipe bent into a serpentine shape or formed into coils, with one purpose: to transfer heat from the refrigerant inside the pipe to the air outside the pipe. It's a heat exchanger, and like all heat exchangers, its effectiveness depends on several factors, including surface area, the temperature difference between the fluids, and the thermal properties of the materials involved. Most condenser coils in household refrigerators are made of copper tubing. Copper is an excellent choice for this application. It has very high thermal conductivity, which means heat flows through it easily. This is important because you want heat to move quickly from the hot refrigerant inside the tube to the outer surface, where it can radiate into the air. Copper is also relatively easy to bend and shape, which allows manufacturers to create the complex coil patterns needed to maximize surface area. And while copper is more expensive than some alternatives, its performance and durability make it worthwhile. In some refrigerators, especially more budget-friendly models, you might find condenser coils made of aluminum tubing instead. Aluminum has lower thermal conductivity than copper, typically around 55 to 60% of copper's conductivity depending on the alloy. This means heat doesn't flow through it quite as easily. However, aluminum is lighter and less expensive, and for many applications, the difference in performance is small enough that the cost savings make it attractive. Some condensers use a combination: copper tubing with aluminum fins attached. Fins are thin sheets of metal, usually aluminum, attached to the condenser tubing. They look like small plates or fins, hence the name, spaced evenly along the length of the tube. These fins dramatically increase the surface area available for heat transfer. Remember, heat transfer from the condenser to the air happens at the surface. The more surface area you have, the more heat you can transfer in a given time. A plain tube might have a surface area of a few hundred square centimeters. Adding fins can increase that to several thousand square centimeters or more, all while keeping the overall size of the unit relatively compact. The fins work because heat conducts from the tube into the fin material and then radiates and convects from the large surface area of the fin into the air. The fins need to be in good thermal contact with the tube, which is usually achieved by press-fitting them onto the tube or by brazing them in place. The spacing between fins is also carefully chosen. If the fins are too close together, air can't flow between them easily, which reduces their effectiveness. If they're too far apart, you're not maximizing the available surface area. Typically, fins are spaced about 5 to 15 millimeters apart, a distance that balances airflow and surface area. The location of the condenser varies depending on the refrigerator design. In many older models and some current ones, the condenser coils are mounted on the back of the refrigerator, exposed to the room. You can see them as a black or copper-colored grid of tubes and fins. These rear-mounted condensers rely entirely on natural convection for cooling. As the condenser coils heat up, they warm the air immediately around them. Warm air is less dense than cool air, so it rises. This creates a gentle upward flow of air past the coils, carrying heat away. Cool air is drawn in from below to replace the rising warm air, creating a continuous circulation. It's a passive process, requiring no fan, no moving parts beyond the refrigerant flow itself. In more modern refrigerators, the condenser is often located at the bottom, underneath the refrigerator, behind a grill or kick plate at the base. This design has aesthetic advantages because the coils are hidden from view, giving the refrigerator a cleaner appearance. Bottom-mounted condensers often include a small fan to force air across the coils. This active cooling is more efficient than natural convection, especially in tight spaces where natural airflow might be restricted. The fan runs whenever the compressor is running, pulling air in through the front grill, pushing it across the condenser coils, and exhausting it out the back or sides. The process happening inside the condenser is fascinating from a thermodynamic perspective. The refrigerant enters as a superheated gas, meaning it's not just a gas, but a gas that's hotter than its boiling point at the current pressure. As it flows through the first portion of the condenser, it begins to cool down. At first, it remains a gas, just a cooler gas, releasing sensible heat. Sensible heat is the heat that causes a change in temperature without a change in phase. You can sense it, feel it, measure it with a thermometer. But as the refrigerant continues through the condenser and continues to cool, eventually it reaches a point where it begins to condense, changing from gas to liquid. This is where latent heat comes into play. The refrigerant releases a large amount of energy during this phase change, even though its temperature remains constant while condensation is occurring. This is latent heat, the hidden heat involved in phase changes. A lot of the heat removed in the condenser comes from this condensation process. By the time the refrigerant exits the condenser, it's mostly liquid, perhaps with a small amount of vapor still mixed in. It's cooled down significantly from the scorching temperatures it had leaving the compressor. In a well-functioning system, the liquid refrigerant leaving the condenser is subcooled, meaning it's cooled below its condensation temperature. This subcooling provides a safety margin, ensuring that only liquid enters the expansion device. If vapor were to enter the expansion device, it would reduce the system's efficiency, because you want as much liquid as possible to evaporate in the evaporator where it's actually doing the cooling. Heat rejection through the condenser is continuous while the compressor is running. The amount of heat rejected is actually more than the amount of heat absorbed from inside the refrigerator. This might seem counterintuitive, but remember, the compressor adds energy to the system. All the electrical energy consumed by the compressor motor ultimately becomes heat, added to the heat that was absorbed from the refrigerator's interior. So if the evaporator absorbs, say, 500 watts of heat from inside the fridge, and the compressor uses 200 watts of electrical power, the condenser must reject about 700 watts total. This is why the area around a refrigerator, especially near the condenser coils, feels warm. It's literally warming your kitchen. Maintenance of the condenser is important for efficiency. Over time, dust, lint, pet hair, and other debris can accumulate on the condenser coils, especially on the fins. This buildup acts as an insulator, reducing the effectiveness of heat transfer. When the condenser can't reject heat efficiently, the pressure in the system rises. The compressor has to work harder, running longer cycles, consuming more electricity. Eventually, if the buildup is severe enough, the system can overheat, potentially damaging the compressor. Cleaning condenser coils is usually straightforward. For rear-mounted coils, you can use a vacuum cleaner with a brush attachment to gently remove dust and debris. For bottom-mounted coils, you might need to remove the front grille to access them. Some refrigerators have coils that are sealed and inaccessible, designed to be maintenance-free, though even these benefit from keeping the surrounding area clean. Manufacturers typically recommend cleaning condenser coils once or twice a year, more frequently if you have pets or live in a dusty environment. The condenser is also where you might find additional heat rejection in some systems. In refrigerators with anti-sweat heaters, small electric heaters are installed around the door frame to prevent condensation from forming on the exterior surface. In high humidity environments, the cold interior surface can cause moisture in the air to condense on the outside of the door, creating that sweaty appearance. The heaters warm the exterior surface slightly, keeping it above the dew point and preventing condensation. These heaters add to the total heat rejected by the refrigerator, though they're typically controlled by a humidity sensor or timer to minimize energy use. The condenser coils might seem simple, just pipes and fins, but they represent a careful balance of engineering considerations. The tubing must be thick enough to withstand the high pressure, but thin enough to transfer heat efficiently. The bends and coils must be smooth to minimize pressure drop and turbulence. The fins must be spaced and sized to maximize heat transfer without impeding airflow. The overall size must be large enough to reject all the necessary heat, but small enough to fit in the available space. Every dimension, every material choice, every detail has been considered and optimized through decades of refinement. And so the condenser does its quiet work. Hot refrigerant flows in, heat radiates out. The refrigerant cools and condenses. And the cycle continues. It's a simple heat exchanger, but it's essential. One of the 4 key components that make refrigeration possible. Without the condenser, there would be nowhere for the heat to go. The refrigerator would quickly overheat, unable to maintain the temperature difference needed to keep food cold. But with a properly designed and maintained condenser, the heat flows steadily outward, dissipating into the surrounding air, allowing the system to function efficiently year after year. After the refrigerant leaves the condenser as a high-pressure liquid, it travels toward the expansion device. This component might seem unimpressive at first glance. In many refrigerators, it's nothing more than a very thin copper tube, perhaps 1 or 2 millimeters in internal diameter, several meters long, coiled up to save space. It has no moving parts, no electrical connections, no controls. And yet, this simple piece of tubing is absolutely critical to the refrigeration cycle. It's where the cold actually begins. The expansion device goes by several names. Sometimes it's called a capillary tube, named after the tiny capillaries in your bloodstream, because like those blood vessels, it's a very narrow tube. Sometimes it's referred to as a metering device, because it meters or controls the flow of refrigerant into the evaporator. In more sophisticated systems, you might find a thermostatic expansion valve instead, which actively regulates flow based on temperature. But in most household refrigerators, a simple capillary tube does the job beautifully. The purpose of the expansion device is to create a pressure drop. Refrigerant enters at high pressure from the condenser and exits at low pressure into the evaporator. This pressure drop is dramatic. The high side of the system might be at 10 or 12 bars of pressure, roughly 10 to 12 times atmospheric pressure. The low side might be at 1 or 2 bars, close to atmospheric, or even slightly below. The expansion device creates this pressure differential, and in doing so, it causes the refrigerant to cool down significantly. How does a narrow tube create such a large pressure drop? It's all about flow resistance. When a fluid flows through a pipe, there's friction between the fluid and the pipe walls. This friction resists the flow and causes a pressure drop along the length of the pipe. In a normal-sized pipe, this pressure drop might be negligible, but in a very narrow pipe, the friction becomes significant. The narrower the pipe, the greater the friction per unit length. And if you make the pipe long enough, that friction adds up to create a substantial pressure drop. The dimensions of a capillary tube are carefully chosen for each refrigerator model. The inside diameter might be anywhere from 0.5 to 2.5 millimeters. That's incredibly small, about the thickness of a paperclip wire or smaller. The length depends on how much pressure drop is needed and on the properties of the refrigerant being used. A typical capillary tube might be anywhere from 1 to 6 meters long. To save space, it's coiled up, often wrapped around other parts of the refrigeration circuit or tucked into the insulation. As liquid refrigerant flows through the capillary tube, several things happen. First, the pressure drops gradually along the length of the tube due to friction. As the pressure drops, the refrigerant's boiling point also drops. Remember, the boiling point of a liquid depends on pressure. Water boils at 100 degrees Celsius at sea level, but at lower pressures, like at high altitude, it boils at a lower temperature. The same principle applies to refrigerant. At high pressure, the refrigerant might have a boiling point of 40 or 50 degrees Celsius. At low pressure, its boiling point might be -20 or -30 degrees Celsius. So as the refrigerant flows through the capillary tube and the pressure drops, eventually the pressure drops below the saturation pressure for the refrigerant's current temperature. At that point, some of the liquid begins to flash into vapor. This is called flash evaporation. It happens suddenly, often partway through the capillary tube. One moment you have liquid refrigerant. The next moment you have a mixture of liquid and vapor, with bubbles of vapor forming throughout the liquid. Flash evaporation requires energy. When a liquid evaporates, it absorbs latent heat from its surroundings. But in the confined space of the capillary tube, the surrounding area is more liquid refrigerant. So the evaporating vapor absorbs heat from the remaining liquid, cooling it down. This is how the expansion device creates cold. By dropping the pressure and causing flash evaporation, it causes the refrigerant to cool itself. By the time the refrigerant exits the capillary tube and enters the evaporator, it's a cold mixture of liquid and vapor, much colder than it was entering the capillary tube. The exact proportions of liquid and vapor depend on the specific operating conditions, but typically it's mostly liquid with perhaps 20 to 30% vapor by mass. This cold mixture is now ready to absorb heat from inside the refrigerator. One of the interesting features of a capillary tube is that it has no moving parts and no feedback mechanism. It doesn't adjust its flow based on temperature or pressure. It simply provides a fixed restriction. The flow rate through it depends entirely on the pressure difference between the inlet and outlet. If the pressure difference increases, more refrigerant flows. If it decreases, less flows. This means a capillary tube works best when the operating conditions are relatively stable. It's designed for a specific range of temperatures and loads. This is why capillary tubes are most common in systems with fairly constant heat loads, like household refrigerators. The refrigerator usually maintains a fairly steady internal temperature, and the ambient temperature in your kitchen doesn't vary wildly from day to day. Under these conditions, a capillary tube provides adequate refrigerant metering at low cost and with no moving parts to fail. In contrast, thermostatic expansion valves are used in systems where the load varies significantly or where precise control is needed. A thermostatic expansion valve, or TXV, has a temperature-sensing bulb attached to the outlet of the evaporator. This bulb is filled with a fluid similar to the refrigerant. As the temperature at the evaporator outlet changes, the pressure in the bulb changes, which moves a diaphragm that opens or closes a valve, adjusting the flow of refrigerant. This feedback loop allows the TXV to maintain a more constant superheat, the amount by which the refrigerant vapor is heated above its boiling point, ensuring efficient operation under varying conditions. TXVs are more complex, more expensive, and have move-in parts that can wear or fail. For a household refrigerator, the added cost and complexity usually aren't justified. A well-designed capillary tube does the job effectively and reliably. It's a passive component that simply lets physics do the work. There are some challenges with capillary tubes, though. Because they're so narrow, they can become clogged by contaminants. Even a tiny particle, a speck of dirt, or a flake of metal from manufacturing can partially or completely block the tube. This is why refrigeration systems include filter dryers, small canisters filled with material that absorbs moisture and filters out particles. The filter dryer is usually located just before the capillary tube, ensuring that only clean, dry refrigerant enters. Moisture is particularly problematic. Water in a refrigeration system can freeze at the cold temperatures in the low-pressure side, forming ice crystals that can block the capillary tube or damage components. Water can also react with refrigerant and oil to form acids, which can corrode metal surfaces. The filter dryer contains a desiccant, a substance that absorbs water, keeping the system dry and preventing these problems. Another interesting aspect of capillary tubes is that they allow pressure equalization when the compressor is off. During normal operation, there's a large pressure difference between the high and low sides of the system. When the compressor stops, this pressure difference begins to equalize. The high-pressure refrigerant flows through the capillary tube into the low-pressure side, gradually evening out the pressures. This equalization is beneficial because it means the compressor doesn't have to start against a large pressure difference. Starting against high pressure requires more torque and more electrical current, which can shorten the compressor's life. By allowing pressures to equalize during off cycles, a capillary tube reduces the stress on the compressor motor. The design of a capillary tube is deceptively simple, but requires careful calculation. Engineers must consider the refrigerant's properties, the desired pressures, the expected flow rates, the length and diameter of the tube, and how all these factors interact. If the tube is too short or too wide, it won't provide enough restriction, and the pressure drop will be insufficient. If it's too long or too narrow, it will provide too much restriction, limiting refrigerant flow and reducing the system's capacity. Computer simulations and empirical testing are used to optimize capillary tube design. Manufacturers have extensive databases of designs for different refrigerants and different system capacities. The tube might be a straight length, or it might be coiled. Sometimes capillary tubes are soldered to the outside of the suction line, the pipe that returns low-pressure vapor from the evaporator to the compressor. This arrangement, called a suction line heat exchanger, provides additional cooling to the liquid refrigerant in the capillary tube and slightly warms the vapor in the suction line, improving efficiency. So this simple tube, this passive component with no moving parts and no controls, performs a critical function. It drops the pressure, it cools the refrigerant, it meters the flow. And it does all of this reliably, silently, for years on end. It's a perfect example of how sometimes the simplest solution is the best solution, how clever design can eliminate complexity and improve reliability. The expansion device might be small and unassuming, but without it, there would be no cold. It's where the heat extraction truly begins, where high pressure becomes low pressure, where warm liquid becomes cold vapor, where the physics of phase changes and pressure drops combine to create the temperatures needed to keep your food fresh. The evaporator is where the refrigerator's real work happens. It's where heat is actually absorbed from the food and air inside the cabinet. After passing through the expansion device, the cold mixture of liquid and vapor refrigerant enters the evaporator coils, and it's here that the final transformation occurs, from liquid to gas, absorbing heat and creating the cold environment we rely on. Like the condenser, the evaporator is essentially a heat exchanger made of coiled tubing. But while the condenser rejects heat to the outside air, the evaporator absorbs heat from the inside air. The construction is similar: copper or aluminum tubing, sometimes with aluminum fins attached to increase surface area. The tubing might be 1/2 inch or so in diameter, bent into serpentine shapes or wrapped around surfaces, designed to maximize contact with the air that needs to be cooled. The location and design of evaporator coils vary significantly depending on the type of refrigerator. In older freezers and some manual defrost models, the evaporator might be a simple coil wrapped around the interior walls of the freezer compartment, visible and often covered with frost. In more modern frost-free refrigerators, the evaporator is hidden behind a panel, usually at the back of the freezer section, with a fan to circulate air across it. Let's follow the refrigerant as it enters the evaporator. It arrives as a cold mixture, perhaps 20% vapor and 80% liquid by mass, at a temperature well below the interior temperature of the refrigerator or freezer. In a freezer, the interior might be around -18 degrees Celsius, 0 degrees Fahrenheit. The refrigerant entering the evaporator might be -25 or -30 degrees Celsius, cold enough to absorb heat even from air that's already below freezing. As the refrigerant flows through the evaporator coils, the liquid portion continues to evaporate. This evaporation is the key to the cooling process. When a liquid evaporates, it absorbs a large amount of energy, the latent heat of vaporization. This energy has to come from somewhere, and it comes from the air and surfaces surrounding the evaporator coils. Heat flows from the warmer air into the colder refrigerant, and the refrigerant uses this heat energy to change phase from liquid to gas. This process is continuous as the refrigerant flows through the evaporator. Liquid evaporates, absorbing heat. The vapor flows onward, making room for more liquid to enter from behind. By the time the refrigerant exits the evaporator, ideally all of the liquid has evaporated, and what remains is pure vapor, slightly warmed from the heat it absorbed, but still much cooler than room temperature. This vapor then returns to the compressor to begin the cycle again. The amount of heat absorbed depends on several factors. First, the temperature difference between the refrigerant and the air. The greater the difference, the faster heat flows. Second, the surface area of the evaporator. More surface area means more contact with the air, allowing more heat transfer. Third, the airflow across the evaporator. Moving air carries heat more effectively than still air, which is why many refrigerators use fans to circulate air across the evaporator coils. In a typical frost-free refrigerator, there's a small fan, called an evaporator fan, located near the evaporator coils in the freezer section. This fan runs whenever the compressor is running, pulling air from both the freezer and refrigerator compartments, forcing it across the cold evaporator coils, and then circulating the cooled air back into the compartments. The airflow is carefully designed to ensure even cooling throughout the refrigerator. There might be vents and dampers that control how much cold air goes to the refrigerator section versus the freezer section, allowing separate temperature control. Frost formation is a natural consequence of evaporator operation. The air inside a refrigerator contains moisture. When this moist air contacts the cold evaporator coils, the moisture condenses and freezes, forming frost. Over time, this frost accumulates, coating the coils with an insulating layer of ice. This frost acts as a barrier to heat transfer, reducing the evaporator's effectiveness. In manual defrost refrigerators, this frost must be periodically removed by turning off the refrigerator and allowing the evaporator to warm up until the ice melts. Frost-free refrigerators automate this process. They include a defrost system that periodically warms the evaporator to melt any accumulated frost. This system typically consists of three components: a defrost heater, a defrost thermostat, and a defrost timer or electronic control. The timer or control determines when defrost should occur, usually every 8 to 12 hours of compressor run time. When it's time for defrost, the compressor and evaporator fan are turned off, and the defrost heater is turned on. The defrost heater is usually an electric resistance heater, a coil of wire that gets hot when current flows through it. It's mounted near or around the evaporator coils. When energized, it warms the coils enough to melt the frost. The melted water drips down into a drain pan, flows through a drain tube, and ends up in a drip tray usually located near the compressor at the bottom of the refrigerator. The heat from the compressor eventually evaporates this water. The defrost thermostat monitors the temperature of the evaporator. When the evaporator warms up enough that all the frost has melted, typically around 4 to 10 degrees Celsius depending on the design, the defrost thermostat signals the control to end the defrost cycle. The heater is turned off, and the compressor and fan resume normal operation. The entire defrost cycle usually takes 20 to 30 minutes. Because it happens when the compressor is off anyway, it has minimal impact on the refrigerator's efficiency, and it ensures that frost never accumulates to the point where it affects performance. The temperature at which the evaporator operates is carefully controlled. In the freezer section, the evaporator needs to be cold enough to maintain freezer temperatures, typically around -20 to -25 degrees Celsius. In refrigerators with separate evaporators for the freezer and refrigerator sections, the refrigerator evaporator operates at warmer temperatures, maybe -5 to 0 degrees Celsius, just cold enough to keep food chilled without freezing. Some refrigerators use a single evaporator for both sections, with dampers and airflow control to manage the temperature difference. Cold air is generated in the freezer section, and some of it is diverted to the refrigerator section. The amount diverted is controlled by a damper, essentially a small door that opens and closes based on signals from the refrigerator's thermostat. When the refrigerator needs more cooling, the damper opens more. When it's cold enough, the damper closes. This allows precise temperature control in both sections with just one evaporator. Evaporator design is a balance of many factors. The coils need to be large enough to absorb all the heat load from the food and air, but small enough to fit in the limited space available. The refrigerant flow rate must be matched to the evaporator's capacity, ensuring that all the liquid evaporates by the time it exits. If liquid refrigerant reaches the compressor, it can cause damage because compressors are designed to compress gas, not liquid. On the other hand, if the refrigerant evaporates too early before reaching the end of the evaporator, you're not using the full capacity of the coils. Engineers aim for a condition called superheat at the evaporator outlet. Superheat means the refrigerant vapor is heated above its boiling point. A few degrees of superheat ensures that all the liquid has evaporated and provides a safety margin against liquid reaching the compressor. But too much superheat means wasted evaporator capacity, because part of the coils is just warming vapor rather than evaporating liquid. The materials used in evaporators are chosen for their thermal conductivity and durability. Copper has excellent thermal conductivity and is corrosion resistant, making it a common choice. Aluminum is lighter and less expensive, though slightly less conductive. Aluminum is often used for fins attached to copper tubes, combining the best properties of both metals. The tubes are usually about 6 to 10 millimeters in outside diameter, a size that balances heat transfer efficiency with structural strength and material cost. Some modern refrigerators use plate-type evaporators, where the refrigerant flows through channels in thin aluminum plates. These offer good heat transfer and can be more compact than traditional coiled tubes. They're often used in the back walls of refrigerators, where they provide cooling directly to the food storage area without the need for fans or moving air. The evaporator is the component that's doing the actual cooling you experience when you open your refrigerator. It's absorbing heat from your food, your drinks, the air, everything inside the cabinet. It's pulling warmth out and sending it away through the refrigerant flow, and it does this continuously while the compressor runs, maintaining those cold temperatures we depend on to keep our food safe and fresh. Think about the evaporator coils as the interface between the refrigeration cycle and your food. They're where the invisible process of heat transfer becomes tangible. You can't see heat moving, but you can feel the cold air blowing from the vents. You can watch frost form on the coils in a manual defrost freezer. You can hear the fan circulating air. These are all signs of the evaporator at work, silently, efficiently, extracting heat molecule by molecule, keeping your ice cream frozen and your lettuce crisp. Refrigerants, the invisible workers. Throughout all of this, we've been talking about refrigerant, this special fluid that flows through the system, changing state, carrying heat. But what exactly is refrigerant? What makes it so special that it can do this job that water or air couldn't do? And how has it evolved over the decades as our understanding of chemistry and environmental science has grown? A refrigerant is any substance used in a heat pump or refrigeration cycle. For it to be useful, it needs several specific properties. First, it needs to have a boiling point in a useful range. It should evaporate at low temperatures when the pressure is reduced, and it should condense at reasonable temperatures when the pressure is increased. Second, it would be able to carry a lot of heat per unit mass, which means a high latent heat of vaporization. Third, it should be stable, not breaking down or reacting with the materials in the system. And fourth, ideally it should be safe for humans and the environment. Finding substances that meet all these criteria has been a challenge throughout the history of refrigeration. Early refrigerators used a variety of refrigerants, some of them quite dangerous. Ammonia was common in commercial systems and still is today in large industrial applications. It's an excellent refrigerant in terms of performance, but it's toxic and flammable, making it unsuitable for household use. Sulfur dioxide was used in some early home refrigerators, but it too is toxic. Methyl chloride, another early refrigerant, was toxic and flammable. In the 1930s, a breakthrough came with the development of chlorofluorocarbons, or CFCs. The most famous of these was dichlorodifluoromethane, commonly known by its trade name Freon 12, or simply R12. R12 was revolutionary for its time. It was non-toxic, non-flammable, chemically stable, and had excellent thermodynamic properties. It quickly became the standard refrigerant for household refrigerators, and remained so for more than half a century. But in the 1970s and 1980s, scientists discovered that CFCs were causing serious environmental damage. When released into the atmosphere, they eventually drifted up into the stratosphere, where ultraviolet light broke them apart, releasing chlorine atoms. These chlorine atoms acted as catalysts, destroying ozone molecules. Ozone in the stratosphere is crucial because it absorbs harmful UV radiation from the sun. The destruction of the ozone layer was leading to increased UV radiation reaching Earth's surface, causing skin cancer and other health problems. In response, The international community came together and signed the Montreal Protocol in 1987, an agreement to phase out the production and use of ozone-depleting substances, including CFCs. This was one of the most successful environmental agreements in history. Manufacturers had to find alternatives, and they did. The first major replacement for R12 in refrigerators was R134A, or tetrafluoroethane. R134A contains no chlorine, so it doesn't deplete the ozone layer. It's non-flammable and has low toxicity. Its thermodynamic properties are reasonably similar to R12, though not identical. Refrigerators designed for R134A require different lubricating oils and slightly different designs, but the transition was manageable. By the mid-1990s, most new refrigerators were using R134A. However, R134A has its own environmental issue. It's a potent greenhouse gas. It has a global warming potential, or GWP, of approximately 1,430 over a 100-year time frame, meaning that releasing 1 kilogram of R134A into the atmosphere has roughly the same warming effect as releasing 1,430 kilograms of carbon dioxide. This is a concern because refrigerant leaks can occur over the lifetime of a refrigerator, and when old refrigerators are disposed of, refrigerant can escape if not properly recovered. This led to the search for even better refrigerants with lower GWP. One solution that's gaining popularity is the use of hydrocarbons, specifically isobutane, also called R600A. Isobutane is a simple organic molecule with 4 carbon atoms. It has excellent thermodynamic properties, zero ozone depletion potential, and a GWP of just 3, essentially negligible. It's also inexpensive and readily available. The main challenge with isobutane is that it's flammable. However, the amount used in a typical refrigerator is small, usually less than 100 grams, less than a quarter pound. This is such a small quantity that even if all of it leaked out into a kitchen, it wouldn't create a significant fire hazard, assuming the room has reasonable ventilation. Strict safety standards and manufacturing practices ensure that systems using isobutane are safe. Many European and Asian manufacturers have been using R600AI for decades, and it's becoming more common in North America as well. Another option is R290, which is propane. Yes, the same propane used in camping stoves and gas grills. Like isobutane, propane is flammable, but has excellent refrigerant properties and very low environmental impact. It's used in some commercial refrigeration applications and is being considered for wider use as regulations continue to evolve. There are also newer synthetic refrigerants being developed, called hydrofluoroolefins, or HFOs. These are similar to HFCs like R134A, but with lower GWP. They're more complex and expensive to produce, but they offer a middle ground between environmental performance and safety concerns about flammability. The refrigerant's properties deeply affect how the refrigeration system operates. Different refrigerants have different boiling points, different heat capacities, different densities. A system designed for one refrigerant won't work properly with a different one unless modifications are made. The compressor, the expansion device, even the amount of oil need to be matched to the specific refrigerant. For example, R12 and R134A have similar but not identical pressure-temperature relationships. At a given temperature, R134A operates at slightly higher pressures than R12. This means compressors and other components need to be rated for those higher pressures. The oils used also differ. R12 works with mineral oil, while R134A requires synthetic oils like polyester because R134A doesn't dissolve well in mineral oil. Hydrocarbons like R600A have different properties again. Isobutane operates at lower pressures than R134AA for the same temperatures. It also has a lower density, which means the mass flow rate of refrigerant needed for the same cooling capacity is less. A refrigerator using R600A might contain only 40 or 50 grams of refrigerant, compared to 150 grams or more for R134A. This lower charge is not only safer, but also reduces the environmental impact if the refrigerant is eventually released. Refrigerants are carefully contained within the sealed system. The refrigeration circuit is assembled and then evacuated to remove all air and moisture. Refrigerant is then charged into the system to a precise amount, usually specified by the manufacturer. Too little refrigerant, and the system won't provide enough cooling. Too much, and the system can be damaged, particularly the compressor, which isn't designed to handle liquid refrigerant. Over the life of a refrigerator, some refrigerant can be lost to very slow leaks through seals and joints. This is why regulations increasingly require that refrigerant be recovered and recycled when appliances are serviced or disposed of. Professional technicians use special equipment to capture the refrigerant from old systems, preventing it from escaping into the atmosphere. The choice of refrigerant is driven by multiple factors: performance, safety, cost, environmental impact, and regulatory requirements. It's a complex balancing act, and as our understanding of environmental science evolves, so too do the refrigerants we use. What's clear is that refrigerants will continue to improve with better performance and lower environmental impact as engineers and chemists continue to innovate. But regardless of which specific refrigerant is inside, the fundamental process remains the same. The refrigerant evaporates, absorbing heat. It's compressed, increasing its pressure and temperature. It condenses, releasing heat. And it expands, dropping in pressure and temperature. This cycle continues, carrying heat from inside to outside, keeping your refrigerator cold, your food fresh, day after day, year after year. While the refrigeration cycle is responsible for extracting heat, insulation is responsible for keeping that heat from coming back in. No matter how efficient your compressor, condenser, and evaporator are, if the refrigerator's walls don't provide good thermal resistance, heat will flow back in as fast as you remove it. Insulation is the unsung hero of refrigerator efficiency, the quiet barrier that makes everything else work. The walls of a refrigerator are essentially a sandwich. On the outside, there's usually a thin sheet of metal, typically steel or stainless steel, painted or coated for appearance and rust protection. On the inside, there's a liner, usually made of plastic, often high-impact polystyrene or ABS plastic. These liners are smooth, easy to clean, and food-safe. Between these two layers is the insulation, a thick layer of material designed to resist heat flow. For decades, the insulation of choice has been rigid polyurethane foam. This foam is remarkable. It consists of a solid matrix of plastic containing countless tiny closed cells, each filled with gas. The cells are so small you can't see them individually, but together they create a structure that's typically around 95 to 98% gas by volume, with the remaining portion being the solid plastic structure. This cellular architecture gives polyurethane foam its excellent insulating properties. Heat can transfer through materials in three ways: conduction, convection, and radiation. Conduction is heat flowing through solid matter. Convection is heat carried by moving fluids like air or water. Radiation is heat traveling as electromagnetic waves, like the warmth you feel from the sun. Good insulation needs to resist all three modes of heat transfer. Polyurethane foam excels at this. The solid plastic matrix resists conduction. But plastic itself isn't that great an insulator. The real magic is in the gas-filled cells. Gas, particularly when trapped in small spaces where it can't move around and create convection currents, is an excellent insulator. The gas molecules move around randomly, colliding with each other and with the cell walls, but there's very little net transfer of heat through the gas. The type of gas in the cells matters. When polyurethane foam is manufactured, it's created through a chemical reaction that produces gases. Originally, CFCs were used as blowing agents, the gases that inflate the foam. When CFCs were banned, manufacturers switched to HCFCs and then to hydrocarbons like cyclopentane or isopentane. These hydrocarbon gases have very low thermal conductivity, even lower than air, which makes them excellent insulators. The foam is injected into the space between the outer shell and inner liner during manufacturing. It starts as a liquid mixture that quickly reacts and expands, foaming up to 30 or 40 times its original volume within seconds. As it expands, it fills every crevice, bonding to both the inner and outer surfaces, creating a single rigid structure. This not only provides insulation, but also adds structural strength, helping the refrigerator hold its shape and support the weight of its contents and doors. The thickness of the insulation varies depending on the refrigerator section and design goals. Typical wall thickness is 40 to 60 millimeters, about 1.5 to 2.5 inches. Freezer compartments, which need to maintain colder temperatures, often have a thicker insulation. The door also contains insulation, though it's usually somewhat thinner to keep the door from being too heavy. The effectiveness of insulation is measured by its R value or U value. R value indicates thermal resistance, how well it resists heat flow. Higher R values mean better insulation. U value is the inverse, the rate of heat transfer. Lower U values mean better insulation. Polyurethane foam typically has an R value of about R6 to R8 per inch of thickness. So a 2-inch thick wall might have an R value of R12 to R16, providing excellent thermal resistance. One challenge with foam insulation is that its performance degrades slightly over time. This happens because the low conductivity gases in the cells gradually diffuse out and are replaced by air from the surroundings. Air has higher thermal conductivity than the hydrocarbon gases, so the insulation becomes slightly less effective. This process is slow, taking years or even decades, but it does occur. To minimize this degradation, manufacturers use plastic liners and outer shells that are less permeable to gases, slowing the diffusion process. An alternative to polyurethane foam is polystyrene foam, which is less expensive but also less effective as an insulator. Polystyrene has larger cells and typically doesn't bond as well to the surrounding surfaces. It's sometimes used in budget refrigerators or in refrigerated shipping containers, but for household refrigerators, polyurethane is preferred for its superior performance. Some high-end refrigerators use vacuum insulation panels or VIPs in addition to or instead of foam. A VIP is a panel from which nearly all the air has been removed, creating a vacuum. Since vacuum contains no gas molecules to conduct heat, it provides extremely high insulation values, R30 or even R40 per inch. VIPs are thin, rigid panels wrapped in gas barrier films to maintain the vacuum. They're expensive and delicate, so they're typically used only where space is at an absolute premium, such as in the very thin walls of some premium refrigerator models. The door seals, or gaskets, are another critical component of the insulation system. These gaskets are usually made of flexible rubber or plastic, with a magnetic strip inside that holds the door closed against the cabinet. The gasket creates an airtight seal, preventing warm air from leaking in when the door is closed. Over time, gaskets can become worn, cracked, or lose their flexibility, reducing their effectiveness. Replacing worn gaskets is one of the most common and effective maintenance tasks for improving refrigerator efficiency. Even the best insulation can't stop heat transfer entirely, only slow it down. There will always be some heat flowing from the warmer kitchen into the colder refrigerator. The refrigeration system must continuously remove this inflowing heat to maintain the temperature. Better insulation means less heat flows in, which means the compressor runs less often, saving energy. This is why modern refrigerators are so much more efficient than those from decades past. A typical refrigerator from the 1970s might have used 1,500 to 2,000 kilowatt-hours of electricity per year, though larger models could use even more. A modern Energy Star certified refrigerator of similar size might use only 300 to 500 kilowatt-hours per year, representing a dramatic improvement of 70 to 80%. Much of this improvement comes from better insulation, though more efficient compressors, better door seals, and improved refrigerants also play significant roles. The insulation in your refrigerator is silent, invisible, unchanging. It sits there day and night, year after year, quietly resisting the flow of heat. It doesn't move, doesn't make noise, doesn't require maintenance, and yet it's absolutely essential. Without it, no amount of refrigeration capacity would be sufficient. The compressor would run constantly, consuming enormous amounts of electricity, barely able to keep up with the inflowing heat. But with good insulation, the refrigerator can maintain its cold interior with only modest energy input, keeping your food fresh efficiently and reliably. Think of insulation as the walls of a fortress, protecting the cold interior from the warm siege outside. The thicker the walls, the better the protection. And inside those walls, the refrigeration cycle works its magic, extracting any heat that does manage to sneak through, maintaining the chill that preserves your food. Door seals and gaskets, the flexible barrier. While the insulation handles the walls, floor, and ceiling of your refrigerator, there's one part that can't be solid insulation because it needs to open and close hundreds of times every week: the door. And yet, when closed, the door must seal as tightly as possible to prevent warm air from leaking in. This is the job of the door gasket, also called the door seal, a deceptively simple component that plays a crucial role in your refrigerator's efficiency. If you run your hand along the edge of your refrigerator door, you'll feel a soft, flexible strip of material that runs all the way around the perimeter. This is the gasket. It's typically made from rubber or a synthetic elastomer, a material chosen for its flexibility, durability, and ability to create an airtight seal. The gasket isn't just a flat strip. It has a specific cross-sectional profile, often shaped like a bulb or tube, designed to compress slightly when the door closes, filling any gaps between the door and the cabinet. Inside most modern gaskets, you'll find a thin magnetic strip. This strip runs the entire length of the gasket, embedded in the rubber. When you close the refrigerator door, this magnetic strip is attracted to the metal cabinet, pulling the door firmly closed and helping to maintain the seal. You can feel this magnetic pull when you open the door, that slight resistance you have to overcome. It's not strong enough to make opening the door difficult, but it's strong enough to keep the door from swinging open on its own and to ensure good contact between the gasket and the cabinet. The seal created by the gasket is remarkably effective when it's in good condition. It prevents the exchange of air between the inside and outside of the refrigerator. This is important for several reasons. First, every time warm air enters the refrigerator, it brings heat that must be removed by the refrigeration system. This makes the compressor run more frequently, consuming more electricity. Second, warm air contains moisture, and when this moisture encounters the cold surfaces inside the refrigerator, it condenses and can form ice, particularly in the freezer section. This ice buildup can insulate the evaporator coils, reducing their effectiveness. The gasket also has to handle significant temperature differences. On the outside, it's exposed to room temperature, perhaps 20 or 25 degrees Celsius. On the inside, particularly where it seals the freezer compartment, it might be exposed to temperatures of -18 degrees Celsius or colder. This 40-degree or greater temperature difference happens across just a few centimeters of material. The gasket material must remain flexible across this entire temperature range. If it becomes brittle in the cold, it won't seal properly. If it becomes too soft in the warmth, it won't maintain its shape. Over time, gaskets can degrade. The rubber or elastomer material can become less flexible, developing cracks or losing its ability to compress and recover. The magnetic strip can weaken. Dirt, food particles, and spills can accumulate on the gasket or on the cabinet surface where it seals, preventing good contact. Mold can grow in the folds of the gasket, particularly in humid environments. All of these issues can compromise the seal, allowing air to leak. You can test your refrigerator's door seal with a simple technique. Close the door on a piece of paper so that half the paper is inside and half is outside. Then try to pull the paper out. You should feel resistance, and the paper should slide out only with a gentle tug. If it slides out easily, or if you can pull it out without the door opening, the seal may be compromised. You can do this test at several points around the door to check the entire gasket. Another method is to shine a flashlight inside the closed refrigerator in a darkened room and look for light leaking out around the edges of the door. Maintaining gaskets is relatively simple but important. Regular cleaning with mild soap and water helps remove dirt and prevents mold growth. Avoid using harsh chemicals or abrasives that could damage the rubber. Some manufacturers recommend applying a thin layer of petroleum jelly to the gasket occasionally to keep it supple and improve the seal. If a gasket is damaged or has lost its effectiveness, it can usually be replaced. Replacement gaskets are available for most refrigerator models, and installing one typically involves removing a retaining strip, pulling out the old gasket, inserting the new one, and replacing the retaining strip. The door itself also contributes to the overall insulation system. Refrigerator doors contain their own layer of insulation, similar to the walls, but typically thinner to keep the door from being too heavy. The door must support its own weight, the weight of whatever's stored in door bins or shelves, and withstand being opened and closed thousands of times. This creates engineering challenges. The door must be strong enough not to warp or sag, which would compromise the seal, yet light enough that the hinges can support it without excessive wear. Most refrigerator doors are made with a metal or plastic outer shell, an inner liner, and foam insulation in between, just like the walls. The hinges are designed to be adjustable, allowing the door to be leveled and aligned properly for a good seal. Over time, hinges can wear or doors can sag slightly, especially on larger refrigerators with heavy doors. Many refrigerators allow for hinge adjustment to correct this, ensuring that the door closes properly and the gasket seals completely all the way around. Some refrigerators have multiple doors or drawers, each with its own gasket and seal. French door refrigerators with two side-by-side doors on the refrigerator section have a vertical seal where the two doors meet in the middle, in addition to the perimeter seals. These center seals face unique challenges because they must seal against each other rather than against a fixed cabinet surface. Side-by-side refrigerators and refrigerators with separate drawers also have multiple sealing surfaces, each of which must function properly for optimal efficiency. The importance of door seals becomes especially clear when you consider the impact of air infiltration. Studies have shown that a poor door seal can increase a refrigerator's energy consumption by 10 to 20% or more. Over the course of a year, this translates to dozens of kilowatt-hours of wasted electricity and several dollars in unnecessary costs. More importantly, a poor seal means the compressor must run more frequently, which increases wear on the system and can shorten the refrigerator's lifespan. In commercial refrigerators, such as those in grocery stores or restaurants, door seals face even greater challenges. These units might have their doors opened dozens or hundreds of times per day. The gaskets must be more durable and are often made from more robust materials. Some commercial units use air curtains, invisible barriers of moving air that help reduce the amount of warm air entering when doors are opened. But the fundamental principle remains the same. Maintaining a good seal when the door is closed is essential for efficiency. So, the next time you close your refrigerator door, take a moment to appreciate that flexible strip of rubber running around the edge. It's working continuously, maintaining a barrier between the cold interior and the warm kitchen, flexing thousands of times as the door opens and closes, resisting temperature extremes and playing its quiet but essential role in keeping your food fresh and your energy bills manageable. Like so many components of a refrigerator, it's a simple thing, easily overlooked, but absolutely necessary for the system to function efficiently. Every refrigerator needs a way to know when to cool and when to rest. This is the job of the temperature control system, the electronic or mechanical brain that monitors conditions inside the cabinet and tells the compressor when to run. In older refrigerators, this was a purely mechanical device called a thermostat. In modern refrigerators, it's often an electronic control board with multiple sensors. But the fundamental purpose remains the same: maintain the desired temperature with minimal energy use. Let's start with the traditional mechanical thermostat, still found in many refrigerators today. This device is elegantly simple, using the physical properties of materials to create a switch that responds to temperature changes. At its heart is a temperature-sensing element, typically a long, thin tube filled with a gas or liquid refrigerant. This tube, called the sensing bulb, is positioned inside the refrigerator, where it can accurately measure the air temperature. The tube is connected to a bellows or diaphragm, a flexible metal component that expands or contracts based on the pressure inside the tube. Here's how it works. As the temperature inside the refrigerator rises, the gas or liquid in the sensing bulb warms up and expands. This expansion increases the pressure inside the bulb and the connected tube. This pressure pushes against the bellows or diaphragm, causing it to move. This movement operates a switch, an electrical contact that completes a circuit and signals the compressor to start running. The compressor runs, removing heat from the refrigerator, and the interior temperature begins to drop. As the temperature drops, the gas or liquid in the sensing bulb cools and contracts. The pressure decreases. The bellows or diaphragm relaxes, moving in the opposite direction. Eventually, the pressure drops enough that the switch opens, breaking the electrical circuit and stopping the compressor. The system then waits as the temperature gradually rises again, due to heat infiltration through the walls and door. When it rises to the set point, the cycle repeats. The set point, the temperature at which the compressor turns on and off, can be adjusted by the user. There's typically a dial or knob marked with numbers or words like colder and warmer. Turning this dial adjusts the physical position of the switch mechanism, changing how much movement of the bellows is needed to close or open the contacts. Setting the dial to colder means the compressor will run more frequently or for longer periods, maintaining a lower average temperature. Setting it to warmer means the compressor will run less frequently, allowing the temperature to rise slightly higher before cooling begins again. This mechanical system includes something called a differential, the difference between the temperature at which the compressor turns on and the temperature at which it turns off. If the compressor turned on and off at exactly the same temperature, it would cycle very rapidly, which would be inefficient and hard on the compressor motor. Instead, there's typically a differential of a few degrees. The compressor might turn on when the temperature reaches 5 degrees Celsius and turn off when it drops to 2 degrees Celsius, for example. This differential provides a dead band, a range of temperatures where no action is taken, allowing for more stable operation and longer compressor run times. Modern electronic temperature controls offer more sophistication and precision. Instead of a mechanical sensing bulb and bellows, electronic systems use thermistors, electronic components whose electrical resistance changes with temperature. A thermistor might be positioned in the refrigerator compartment, another in the freezer, and sometimes additional ones in various locations to monitor different zones. These thermistors are connected to a control board, essentially a small computer dedicated to managing the refrigerator's operation. The control board receives signals from the thermistors, processes this information, and makes decisions about when to run the compressor, when to activate fans, when to initiate defrost cycles, and how to manage other functions. Electronic controls can implement more complex logic than mechanical thermostats. They can average temperatures over time to avoid reacting to brief temperature spikes, such as when the door is opened. They can optimize compressor run times based on patterns of use. They can provide more precise temperature control, maintaining the interior within a tighter range of temperatures. Some advanced electronic systems use variable speed compressors, which we touched on earlier. Instead of simply turning the compressor on or off, these systems can adjust the compressor's speed to match the cooling load. If only a small amount of cooling is needed, the compressor runs slowly. If more cooling is needed, it speeds up. This provides even better temperature stability and improved efficiency because the compressor can run continuously at lower speeds rather than cycling on and off at full power. Electronic controls also enable features like rapid cooling or quick chill modes, where the refrigerator runs the compressor more aggressively for a period of time to quickly lower the temperature, useful when you've just added a large amount of warm food. They can manage separate temperature zones, allowing the refrigerator compartment and freezer compartment to be controlled independently with precision. They can provide digital temperature displays, showing the actual temperature inside rather than just a relative setting. Temperature control systems must also account for the defrost cycle in frost-free refrigerators. As we discussed earlier, the evaporator must be periodically warmed to melt accumulated frost. The control system manages this timing. In older systems, a mechanical defrost timer, basically a small motor-driven clock, keeps track of compressor run time and initiates defrost at regular intervals. In modern electronic systems, the control board performs this function, often using more sophisticated algorithms that base defrost timing on actual conditions rather than just elapsed time. Some refrigerators include adaptive defrost systems that monitor how quickly frost accumulates and adjust the frequency of defrost cycles accordingly. If the refrigerator is in a dry environment and frost accumulates slowly, defrost cycles might occur less frequently, saving energy. If it's in a humid environment or the door is opened frequently, defrost might happen more often. This adaptability improves efficiency while ensuring that frost never builds up enough to affect performance. The location of temperature sensors is carefully considered during refrigerator design. The sensor needs to be positioned where it can accurately reflect the average temperature of the stored food, not too close to the evaporator where it might read artificially cold, and not too close to the door where it might be affected by warm air infiltration during door openings. Some refrigerators use multiple sensors and average their readings to get a more accurate picture of the overall temperature distribution. Temperature control also interacts with other refrigerator features. In refrigerators with ice makers, the control system must manage the ice-making cycle, monitoring when the ice bin is full and stopping ice production, then resuming when space becomes available. In refrigerators with water dispensers, the system might chill water to a specific temperature. In models with humidity-controlled drawers, the system manages not just temperature, but also moisture levels in specific compartments. One often overlooked aspect of temperature control is how it responds to real-world usage patterns. Every time you open the refrigerator door, warm air rushes in. A responsive control system detects this temperature rise and extends the compressor run time slightly to compensate. But it also needs to be smart enough not to overreact to brief door openings. If it started the compressor every time the door was opened for a few seconds, the compressor would cycle too frequently. Good control systems have logic built in to distinguish between minor temperature fluctuations that will naturally correct and significant temperature rises that require active cooling. The control system also plays a role in energy efficiency beyond just managing when the compressor runs. By maintaining consistent temperatures, it prevents food from freezing in the refrigerator section or thawing in the freezer section, both of which would compromise food quality and potentially safety. By optimizing defrost cycles, it prevents excessive frost buildup that would insulate the evaporator and reduce efficiency. By coordinating the operation of the compressor and fans, it ensures that cooling is distributed effectively throughout the cabinet. In the quietness of your kitchen, especially at night, you might hear the click of a thermostat activating, signaling the compressor to start, or the soft beep of an electronic control board acknowledging a command. These sounds are the voice of the control system, the brain of your refrigerator, making decisions and adjustments continuously to maintain that perfect balance between cold preservation and energy efficiency. It's monitoring, evaluating, responding, ensuring that when you reach for that carton of milk in the morning, it's exactly as cold as it should be. To truly appreciate your modern refrigerator, it helps to understand where it came from, the long journey of innovation and discovery that led to the appliance humming in your kitchen. The story of refrigeration is a story of humanity's quest to preserve food, to extend the brief window between harvest and spoilage, to conquer one of nature's most fundamental challenges. For most of human history, keeping food cold meant keeping it in naturally cold places. Underground cellars stayed cooler than the surface, especially in climates with cold winters. Ice and snow, when available, could be packed around food for temporary preservation. In ancient Persia, ingenious structures called yakchals, domed buildings with thick walls and underground storage spaces, used evaporative cooling and careful design to create and store ice even in desert climates. These structures could keep ice frozen through hot summers, providing a cool place for food storage. Ice harvesting became a significant industry in colder regions. During winter, workers would cut large blocks of ice from frozen lakes and rivers, then store these blocks in insulated ice houses, buildings packed with sawdust, straw, or other insulating materials. The ice could last well into summer, providing a source of cooling for homes and businesses. By the 19th century, ice harvesting and distribution was a major commercial enterprise, particularly in the United States. Ice from northern states was shipped as far as the Caribbean and India, packed in sawdust and straw for insulation. Ice boxes, the precursors to modern refrigerators, appeared in the early 1800s. These were insulated cabinets, typically made of wood with zinc or tin linings, containing a compartment for a block of ice and separate compartments for food. The ice would slowly melt, absorbing heat from the food and keeping it cool. A drain at the bottom would catch the meltwater, which had to be emptied regularly. Ice boxes required regular delivery of ice, usually every few days, making ice delivery a common service in cities and towns. But the dream was mechanical refrigeration, a way to create cold without depending on harvested ice. The principles were understood fairly early. In the 1750s, William Cullen at the University of Edinburgh demonstrated that evaporating a liquid could absorb heat and create cold. In 1805, Oliver Evans, an American inventor, designed but never built a refrigeration machine based on vapor compression. Jacob Perkins, working in London, built the first practical vapor compression refrigeration system in 1834, using ether as the refrigerant. It was a breakthrough, but the technology was expensive, complex, and not immediately practical for home use. Throughout the 19th century, various inventors improved refrigeration technology. John Gorey in Florida developed an ice-making machine in the 1840s, intended to cool hospital rooms for patients with yellow fever. Ferdinand Carré in France improved the absorption refrigeration cycle in the 1850s. Carl von Linde in Germany developed a reliable ammonia-based compression refrigeration system in 1876, which became the basis for commercial refrigeration. These systems were large, expensive, and mostly used in industry, in breweries, meat packing plants, and for ice production. The domestic refrigerator, the kind you might have in your home, didn't really emerge until the early 20th century. In 1913, Fred W. Wolfe of Fort Wayne, Indiana, introduced a refrigerator for home use called the Dommelre, which stood on top of an icebox. In 1916, Alfred Mellows designed a self-contained refrigerator with a compressor and icebox in a single unit. William C. Durant purchased Mellows Company and renamed it Frigidaire, which would become one of the most recognizable names in refrigeration. General Electric introduced the Monitor Top refrigerator in 1927, so named because the compressor unit mounted on top resembled the gun turret on the Civil War ship USS Monitor. This model was popular and helped bring electric refrigeration to more households, though it was still expensive, costing several $100s when the average yearly income was around $1,500. Throughout the 1920s and 1930s, refrigerators became more common, more affordable, and more reliable. Designs improved. Noise levels decreased. Refrigerants evolved, with the development of CFCs in the 1930s, providing safer, non-toxic alternatives to ammonia and sulfur dioxide. By the 1940s and 1950s, refrigerators had become standard appliances in American homes, with ownership rates climbing from around 50% in 1940 to nearly 90% by 1950. The post-World War II economic boom, combined with suburban development and the growth of supermarkets, made refrigerators not just desirable, but nearly essential for modern life. Designs became more stylish, with manufacturers offering refrigerators in colors with chrome trim in various sizes and configurations. The freezer compartment became standard. Early refrigerators had only small freezing compartments, barely large enough for a few ice cube trays. But as frozen food became more popular in the 1940s and 1950s, larger freezer sections became important. Two-door refrigerators with separate freezer and refrigerator compartments, each with its own door, appeared in the late 1940s and became increasingly common. Side-by-side refrigerators, with the freezer on one side and the refrigerator on the other, were introduced in the 1960s, offering easier access to both sections. Automatic defrost was a major innovation, eliminating the need to periodically turn off the refrigerator and manually remove ice buildup. The first automatic defrost refrigerators appeared in the 1950s, though the technology took some time to mature. Frost-free operation, as we know it today, became standard by the 1970s in most refrigerators. This feature alone probably did more to improve the user experience than almost any other innovation, turning the refrigerator from an appliance that required regular maintenance into one that could simply run unattended for years. Energy efficiency became a focus starting in the 1970s, driven by oil crises and growing awareness of energy costs. Government regulations, particularly the National Appliance Energy Conservation Act in the United States in 1987, set minimum efficiency standards and drove manufacturers to improve insulation, compressor efficiency, and overall design. As we've noted, refrigerators today use a fraction of the energy of models from the 1970s, despite being larger and having more features. The environmental movement also drove changes in refrigerants, moving away from CFCs to HCFCs, and then to HFCs, and now to natural refrigerants like hydrocarbons. Each transition required redesigning refrigeration systems, developing new oils and lubricants, and ensuring safety and performance. The industry adapted, driven by regulation, competition, and the growing importance consumers placed on environmental responsibility. Today's refrigerators are technological marvels compared to those early ice boxes, and even compared to refrigerators from just a few decades ago. They have electronic controls, variable speed compressors, LED lighting, water and ice dispensers, smart features that connect to the internet. And yet, at their core, they still use the same vapor compression cycle that Carl von Linde pioneered in the 1870s. It's a testament to the fundamental soundness of that technology that it remains, after more than a century, the best way we have to keep food cold in our homes. The journey from icehouse to smart refrigerator has taken thousands of years, if we count the history of cold storage, and about 150 years for mechanical refrigeration. It's a journey driven by necessity, enabled by science, and refined by engineering. And it continues. Researchers are still working on better insulation, more efficient compressors, alternative refrigeration technologies, improved materials. The refrigerator in your kitchen is not the end of this story. It's just the current chapter, a milestone on a continuing path of innovation. Now that we've explored each component individually, let's step back and watch the whole system work together. Imagine we could follow a single heat energy packet as it's extracted from inside your refrigerator and expelled into your kitchen. Where does it begin? Where does it go? How does each component contribute to this journey? Our story begins with a cold apple sitting on a shelf inside your refrigerator. The apple, like all matter above absolute zero, contains thermal energy. Its molecules are vibrating, moving, colliding with one another. This energy, this heat, wants to spread out, to equilibrate with its surroundings. But the refrigerator works to prevent this. The air inside the refrigerator is kept at about 3 or 4 degrees Celsius, 37 or 38 degrees Fahrenheit. The evaporator coils, hidden behind a panel at the back of the freezer section, are even colder, perhaps minus 20 degrees Celsius. A small fan circulates air through the refrigerator. Air from around the apple is drawn back toward the evaporator. As this air passes over the cold evaporator coils, heat transfers from the air to the coils. The air cools down and is circulated back into the refrigerator. Meanwhile, the heat that was in that air is now being absorbed by the refrigerant inside the evaporator coils. The refrigerant in the evaporator is a mixture of liquid and vapor, very cold, maintained at low pressure by the action of the compressor continuously pulling vapor away. As heat from the air transfers through the metal tube walls into the refrigerant, the liquid refrigerant absorbs this energy and evaporates, changing from liquid to gas. This phase change consumes a lot of energy, the latent heat of vaporization, allowing the refrigerant to absorb substantial heat while remaining at a constant temperature. The newly formed vapor, now carrying the heat that was absorbed from the air that was around the apple, flows through the evaporator coil toward the outlet. By the time it reaches the end of the evaporator, all the liquid has evaporated, and the vapor is slightly superheated, warmed a few degrees above its boiling point for that pressure. This superheated vapor then flows through the suction line toward the compressor. The compressor's motor is running, its pistons or rotors working steadily. Low-pressure vapor enters the compressor's intake. The compression process begins. The volume of the vapor is reduced, the molecules pushed closer together. This compression requires work, energy input from the electric motor. That energy also becomes heat, adding to the heat the refrigerant already contains. The result is hot, high-pressure vapor leaving the compressor at temperatures that might exceed 60 or 70 degrees Celsius, much hotter than the kitchen air. This hot vapor flows through the discharge line into the condenser coils at the back or bottom of the refrigerator. The condenser coils are exposed to the kitchen air, which is maybe 20 or 25 degrees Celsius. Because the refrigerant is so much hotter than the air, heat flows from the refrigerant through the metal tube walls into the surrounding air. The metal, usually copper or aluminum, conducts heat well. Fins attached to the tubing increase the surface area, enhancing this heat transfer. As the refrigerant flows through the condenser and releases heat, it cools down. Eventually, it cools enough that it begins to condense, changing from vapor to liquid. This phase change releases latent heat, a substantial amount of energy that flows out into the room. By the time the refrigerant exits the condenser, it's mostly liquid, subcooled below its condensation temperature, and ready for the next stage. This liquid, still at high pressure, flows toward the expansion device. Let's say this refrigerator uses a capillary tube. The liquid enters the narrow tube. Immediately, the restriction of the tiny passageway creates flow resistance. Pressure begins to drop along the length of the tube. As the pressure drops, so does the boiling point of the refrigerant. Eventually, a point is reached where the pressure has dropped low enough that some of the liquid flashes into vapor. This flash evaporation cools the refrigerant, absorbing energy from the remaining liquid. By the time the refrigerant exits the capillary tube, it's a cold mixture of liquid droplets and vapor bubbles, ready to enter the evaporator and begin absorbing heat again. And the cycle continues, around and around, moving heat from inside to outside, from the apple's warmth to the kitchen's air, maintaining the cold interior that keeps food fresh. But there's more happening than just the refrigeration cycle. The thermostat, or electronic control, is constantly monitoring temperatures. When the temperature inside rises above the set point, it signals the compressor to start. When the temperature drops below the set point, it signals the compressor to stop. This cycling maintains the temperature within a few degrees of the target, balancing energy use with cooling needs. Meanwhile, every time you open the door, warm air rushes in. The refrigerator's temperature rises slightly. The thermostat detects this and keeps the compressor running a bit longer to remove the added heat. The lights inside the refrigerator also generate small amounts of heat when they're on. Even the metabolic processes of the food itself, fruits and vegetables continuing to ripen and respire, generate tiny amounts of heat that must be removed. The insulation works continuously to slow heat infiltration through the walls. Even so, some heat does conduct through, especially if the kitchen is hot. A poorly sealed door gasket lets air leak in. All of this heat must be dealt with by the refrigeration system, removed and expelled to keep the interior cold. The defrost system activates periodically, warming the evaporator to melt any accumulated frost. The melted water drains away, and normal cooling resumes. This prevents ice buildup that would insulate the evaporator and reduce its efficiency. In a well-designed frost-free system, you never notice these defrost cycles. They happen automatically, maintaining optimal performance without any intervention. All these systems work together harmoniously. The compressor provides the energy and pressure difference. The condenser rejects heat to the outside. The expansion device creates the pressure drop and cooling. The evaporator absorbs heat from the inside. The insulation slows heat infiltration. The controls manage cycling and defrost. The fans circulate air. Every component has its role, and when they all function properly, the result is a reliable, efficient appliance that keeps your food cold year after year with minimal fuss. It's a dance, a coordinated interplay of thermodynamics, mechanics, electronics, and materials science. Heat flows from warm to cold, but the refrigerator cleverly manipulates pressures and phases to make heat flow where it's needed, from cold to warm. Energy is added at the compressor, transformed and transported by the refrigerant, and ultimately released at the condenser. And through it all, the second law of thermodynamics is satisfied, because the total entropy of the system plus surroundings increases, even as we create a colder space inside the refrigerator. A refrigerator is designed to run for many years with minimal attention, but like any machine, It benefits from proper care and occasional maintenance. Understanding what maintenance your refrigerator needs and what signs might indicate problems can help ensure it operates efficiently throughout its lifespan and alert you to issues before they become serious. The most important and most often neglected maintenance task is cleaning the condenser coils. As we discussed earlier, these coils reject heat to the surrounding air. When they're covered with dust, pet hair, lint, and other debris, they can't transfer heat efficiently. This forces the compressor to run longer and work harder, consuming more energy and potentially shortening its life. For refrigerators with accessible condenser coils, either at the back or at the bottom behind a grill, cleaning should be done at least twice a year, or more frequently if you have pets that shed or if your home is dusty. Cleaning condenser coils is straightforward. First, unplug the refrigerator or turn off its circuit breaker for safety. If the coils are on the back, pull the refrigerator away from the wall carefully. You may need help with this, as refrigerators are heavy. Use a vacuum cleaner with a brush attachment or a special coil cleaning brush to gently remove dust and debris from the coils and fins. Be gentle, as the fins are thin and can bend. For bottom-mounted coils, remove the front grill, usually held by clips or screws, and use a long-handled brush or vacuum attachment to clean the coils. After cleaning, replace the grill and push the refrigerator back into position if you moved it. Door gaskets require attention as well. Every few months, inspect the gaskets for cracks, tears, or deformities. Clean them with mild soap and warm water to remove dirt, food residue, and mold. Make sure the surface of the cabinet that the gasket seals against is also clean. A dirty gasket or cabinet surface can prevent a good seal, even if the gasket itself is in good condition. Some people apply a thin coat of petroleum jelly to the gasket after cleaning to help keep it supple and improve the seal, though this isn't always necessary. The drain hole and drain pan in frost-free refrigerators can sometimes become clogged or dirty. During the defrost cycle, melted frost water drains through a small hole and tube to a pan, usually located at the bottom near the compressor where it evaporates. If this drain becomes clogged with food particles or ice, water can back up and leak into the refrigerator or onto the floor. Periodically, perhaps once or twice a year, locate the drain hole, usually at the back of the refrigerator compartment or freezer, and flush it with warm water using a turkey baster or small funnel. The drain pan should also be checked occasionally and cleaned if it has accumulated dirt or has developed odors. Temperature settings should be verified periodically with an actual thermometer, not just trusted to the refrigerator's display or dial setting. The refrigerator compartment should generally be kept between 1 and 4 degrees Celsius, 34 to 40 degrees Fahrenheit. The freezer should be at or below -18 degrees Celsius, 0 degrees Fahrenheit. If temperatures are higher than these ranges, food safety can be compromised. If they're significantly lower, you're wasting energy and may be freezing foods in the refrigerator compartment that shouldn't be frozen. Interior cleaning is important for hygiene and can also affect efficiency. Spills should be wiped up promptly to prevent odors and bacterial growth. Every few months, remove all food and shelves and clean the interior thoroughly with a mild solution of baking soda and water, which cleans effectively without leaving harsh chemical residues. Make sure drain holes are clear. Clean the door bins and drawers. A clean refrigerator not only looks better, but can also operate more efficiently, as air can circulate more freely without obstructions from spills and buildup. The area around the refrigerator should allow for adequate ventilation. If a refrigerator is pushed too tightly into a space, especially one with rear-mounted condenser coils, it can't dissipate heat effectively. Most manufacturers recommend leaving a small gap, perhaps an inch or two, between the back of the refrigerator and the wall, and some clearance at the sides if possible. Built-in refrigerators are designed differently, with ventilation considerations built into their design, but freestanding units need some space to breathe. Be attentive to unusual sounds or behaviors. Refrigerators do make various sounds during normal operation. The hum of the compressor, the click of the thermostat, the whoosh of fans, the gurgling of refrigerant, the crack of ice expanding or contracting. But new sounds, or sounds that are much louder than usual, can indicate problems. A loud buzzing might indicate a fan hitting something or failing. Constant running without cycling off could mean a control problem, a refrigerant leak, or a failing compressor. Clicking sounds that repeat rapidly might indicate a problem with the start relay. Water pooling inside or outside the refrigerator could indicate a clogged drain or a failing door seal. Many modern refrigerators have diagnostic modes that can display error codes if something is wrong. Consult your owner's manual for information on how to access these modes and what the codes mean. Some problems can be resolved with simple fixes, like replacing a door switch or cleaning a sensor. Others may require professional service. Knowing what's wrong can help you decide whether to attempt to fix yourself or call a technician. Energy consumption is worth monitoring, especially if you suspect a problem. If your electricity bills suddenly increase without an obvious reason, the refrigerator could be working harder than normal due to a failing component, a bad door seal, or dirty condenser coils. Some modern refrigerators have energy monitoring features built in, and there are plug-in electricity monitors you can use to measure how much power an appliance is consuming. Comparing this to the rated power consumption on the refrigerator's data plate can tell you if something's wrong. Knowing when to repair versus replace is an important consideration. Refrigerators can last 15 to 20 years or more with proper maintenance, but eventually, all appliances reach the end of their useful life. Major repairs, particularly to sealed system components like the compressor or evaporator coils, can be expensive, sometimes costing as much as half the price of a new refrigerator. If a refrigerator is old and requires expensive repairs, and especially if it's also energy inefficient by modern standards, replacement might be more cost-effective in the long run than repair. Some repairs are straightforward enough that a handy homeowner can tackle them. Replacing a door gasket, changing a light bulb, replacing a door switch, or cleaning components are all typically manageable with basic tools and patience. But working on sealed refrigeration components requires specialized tools, knowledge, and often certification to handle refrigerants safely and legally. For these repairs, professional service is necessary. Regular maintenance doesn't just keep a refrigerator running. It keeps it running efficiently, which saves money and energy. It extends the lifespan of the appliance, delaying the environmental impact and cost of manufacturing, and disposing of a large appliance, and it helps ensure food safety by maintaining proper temperatures and preventing contamination from mold or bacterial growth. A little attention, perhaps an hour or two of maintenance per year, can pay dividends in performance, efficiency, and longevity. When you look at your refrigerator, you see an appliance that keeps food cold. But zoom out a bit, and you see something more. A device that consumes energy continuously, day and night, year after year. Over its lifetime, a refrigerator uses thousands of kilowatt-hours of electricity. This electricity comes from power plants, which in many parts of the world still burn fossil fuels, producing carbon dioxide and contributing to climate change. The refrigerator itself contains materials, metals, plastics, foam that were extracted from the earth, processed, manufactured, and transported. And eventually it will be disposed of, hopefully recycled, but contributing to waste streams nonetheless. Understanding the energy efficiency and environmental impact of refrigerators helps us appreciate the importance of choosing efficient models and maintaining them properly. Let's start with energy consumption. As we've mentioned, a typical modern refrigerator might use 300 to 500 kilowatt-hours per year, though this varies widely based on size, features, and efficiency. To put this in perspective, if your refrigerator uses 400 kilowatt-hours per year and electricity costs 12 cents per kilowatt-hour, that's about $48 per year in electricity costs. Over a 15-year lifespan, that's $720. This operating cost is in addition to the purchase price of the refrigerator itself. A refrigerator that costs $200 more to purchase but uses 100 kilowatt-hours less per year will save you $12 per year in electricity, paying for itself in about 17 years. If its lifespan is 20 years, you come out ahead. But energy efficiency isn't just about operating costs. It's also about environmental impact. Every kilowatt-hour of electricity typically produces around 0.4 to 0.5 kilograms of carbon dioxide, depending on your local power generation mix. A refrigerator using 400 kilowatt-hours per year is responsible for roughly 160 to 200 kilograms of CO2 emissions annually. Over 15 years, that's 2,400 to 3,000 kilograms, or 2.4 to 3 metric tons. An inefficient refrigerator using twice that energy would double these emissions. Choosing an efficient model matters not just for your wallet, but for the planet. Energy Star is a program run by the U.S. Environmental Protection Agency and Department of Energy that certifies appliances meeting strict energy efficiency criteria. A refrigerator earning the Energy Star label uses at least 10% less energy than required by federal standards. In other countries, similar programs exist, like the EU Energy Label in Europe or energy rating labels in Australia. These labels provide consumers with standardized information about energy consumption, making it easier to compare models and choose efficient options. What makes one refrigerator more efficient than another? Several factors. Better insulation reduces the amount of heat that leaks in, reducing the cooling load. More efficient compressors convert more of their electrical input into useful cooling work, rather than waste heat. Variable speed compressors that can modulate their output are more efficient than fixed speed compressors that simply cycle on and off. Better door seals prevent air infiltration. Smart controls optimize operation. High-efficiency lighting uses LEDs instead of incandescent bulbs, reducing heat generation inside the cabinet. Even small details, like the color and finish of the interior, can matter, with lighter colors reflecting more light and potentially requiring less lighting energy. The refrigerant itself has environmental implications. We discussed earlier how CFCs were phased out due to ozone depletion, and how current refrigerants like R134A have high global warming potential. The ongoing transition to lower GWP refrigerants like hydrocarbons is part of global efforts to combat climate change. The Kigali Amendment to the Montreal Protocol, adopted in 2016, set targets for reducing HFC production and use worldwide. As refrigerant regulations continue to evolve, newer refrigerators increasingly use more environmentally friendly refrigerants. Manufacturing a refrigerator also has environmental costs. The steel, aluminum, copper, and plastics all require energy and resources to produce. The foam insulation, while highly effective, is typically made from petroleum-based chemicals. The processes of stamping sheet metal, molding plastic, assembling components, and shipping the finished product all consume energy. Life cycle assessments, which attempt to quantify the total environmental impact of a product from raw material extraction through end-of-life disposal, show that for refrigerators, the majority of the impact typically comes from the energy consumed during the use phase, rather than manufacturing. But manufacturing is still significant. This is why keeping a refrigerator running efficiently for its full potential lifespan is environmentally beneficial. Premature replacement means the environmental costs of manufacturing a new refrigerator are incurred sooner, and the old refrigerator must be disposed of. If an existing refrigerator can be kept running efficiently through proper maintenance, that's generally better environmentally than replacing it with a slightly more efficient new model. At least until the efficiency gap becomes very large, or the old refrigerator is nearing the end of its useful life anyway. When a refrigerator does reach the end of its life, proper recycling is important. Refrigerators contain materials that are valuable and recyclable, including metals, plastics, and glass. But they also contain refrigerant and oil that must be properly recovered to prevent environmental release. In many jurisdictions, it's illegal to simply throw away a refrigerator or to vent refrigerant to the atmosphere. Professional appliance recyclers have equipment to safely recover refrigerants, remove oils, separate materials, and recycle components. Foam insulation, which often contains blowing agents that shouldn't be released, requires special handling. Responsible disposal ensures that valuable materials are recovered and harmful substances are kept out of the environment. Some refrigerators are refurbished and resold, extending their useful life in a different home. This is generally a good outcome environmentally, assuming the refrigerator is still reasonably efficient and in good working condition. Older, highly inefficient refrigerators are sometimes retired through utility company programs that offer rebates or incentives for replacement with Energy Star models. These programs recognize that the energy savings from replacing a very old, inefficient refrigerator can be substantial, offsetting the environmental costs of manufacturing a new one relatively quickly. The future of refrigerator efficiency likely involves continued improvements in all areas, better insulation materials, more efficient compressors and motors, improved controls, lower GWP refrigerants, and perhaps eventually adoption of alternative refrigeration technologies if they can match or exceed the efficiency and reliability of vapor compression. Consumer awareness and demand for efficient models drive manufacturers to innovate. Government regulations set minimum standards and push the industry forward. And the cumulative effect, millions of households choosing and maintaining efficient refrigerators, makes a measurable difference in energy consumption and environmental impact. So when you think about your refrigerator, think not just about the food inside, but about the energy flowing through the walls, the electricity coming from distant power plants, the refrigerant sealed in the system, the materials that will someday need to be recycled. Your refrigerator is part of a larger system, connected to power grids, to manufacturing facilities, to global efforts to address climate change. Choosing an efficient model, maintaining it properly, and disposing of it responsibly when the time comes are all ways to minimize your refrigerator's environmental footprint. Refrigerator technology hasn't stood still. While the basic vapor compression cycle has remained largely unchanged for a century, countless refinements and innovations have improved efficiency, reliability, and convenience. Modern refrigerators are marvels of engineering optimization, the result of decades of incremental improvements guided by competition, regulation, and consumer demands. One significant innovation is the variable speed compressor. Traditional compressors are either on or off, running at full capacity or not at all. But what if the compressor could adjust its speed to match the cooling load? When cooling demand is low, the compressor could run more slowly, using less electricity. When demand is high, it could speed up. This is what variable speed or inverter-driven compressors do. These compressors use electronic controls to vary the frequency of the alternating current supplied to the motor, allowing the motor to run at different speeds. Instead of cycling on and off, the compressor runs continuously at whatever speed is needed to maintain the desired temperature. This has several advantages. It's more efficient because you avoid the energy spikes associated with starting the motor. It provides more consistent temperatures because the cooling is continuous rather than cyclical. And it's quieter because there are no sudden starts and stops. Smart controls and sensors have also improved performance. Modern refrigerators can monitor multiple temperature zones, adjusting cooling to different compartments independently. They can sense when the door has been opened and compensate by running a bit longer. Some models have humidity sensors that adjust airflow to maintain optimal moisture levels for different types of food. Internet-connected smart refrigerators can send alerts to your phone if temperatures rise unexpectedly or if the door has been left open. Insulation technology continues to advance. While polyurethane foam remains standard, improvements in foam chemistry and manufacturing have increased R values while reducing environmental impact. Vacuum insulation panels, once exotic and expensive, are becoming more common, allowing thinner walls and more interior space. Researchers are exploring aerogel insulations, materials with even better insulating properties, though these remain too expensive for widespread use. Material science has improved other components as well. Compressor bearings are more durable. Seals and gaskets last longer and seal better. Condensers and evaporators are designed with computational fluid dynamics to optimize airflow and heat transfer. Every aspect of the refrigerator is subject to ongoing refinement. Energy efficiency has been a major driver of innovation. Government regulations, particularly Energy Star ratings in the United States and similar programs elsewhere, have pushed manufacturers to continuously improve efficiency. These programs set minimum standards and provide certifications for appliances that exceed those standards, giving consumers information to make informed choices and incentivizing manufacturers to compete on efficiency. The results have been dramatic. As we explored earlier, a typical refrigerator today uses a fraction of the electricity of comparable models from the 1970s or 1980s, often around 70 to 80% less, despite being larger and having more features. This doesn't just save consumers money on their electric bills, it reduces the overall energy demand on the electrical grid, decreasing the need for power generation and the associated environmental impacts. Looking forward, several trends appear likely to continue based on current industry developments. Refrigerants will likely continue to evolve toward lower global warming potential, with natural refrigerants like hydrocarbons becoming increasingly common as safety standards and manufacturing techniques improve. Efficiency improvements are expected to continue through better insulation, more efficient compressors, and smarter controls. Integration with home automation systems will likely provide more convenience and energy management capabilities, and ongoing advances in materials science may enable new designs that are lighter, more durable, and more sustainable. There's also interest in alternative refrigeration technologies beyond vapor compression. Magnetic refrigeration, which uses the magnetocaloric effect where certain materials heat up when magnetized and cool down when demagnetized, has shown promise in laboratory research, but hasn't yet reached commercial viability for household refrigerators. Thermoelectric cooling, based on the Peltier effect, is used in some small applications like portable coolers and wine refrigerators, but currently remains less efficient than vapor compression for larger systems. Still, research continues in these areas, and future breakthroughs could potentially change the landscape of refrigeration technology. For now, though, the vapor compression cycle reigns supreme. It's proven, reliable, efficient, and continuously improving. The refrigerator humming quietly in your kitchen is the culmination of over a century of engineering development, a sophisticated machine that performs a seemingly simple task with remarkable effectiveness. It keeps your food cold, but in doing so, it demonstrates mastery over thermodynamics, precision in manufacturing, and the culmination of countless innovations great and small. And so we come to the end of our journey through the inner workings of refrigerators. We've followed heat from inside to outside, watched compressors squeeze gases, seen condensers reject warmth, explored tiny tubes that create cold, and understood evaporators that absorb heat. We've learned about refrigerants that change state, insulation that resists heat flow, and the elegant cycle that ties it all together. Perhaps you're already drifting into sleep, your breathing slow and steady, your mind wandering through dreams of coils and compressors, of molecules bouncing and pressures dropping. Or perhaps you're still awake, pondering these ideas, appreciating the ingenuity that goes into an appliance so common we barely notice it. Either way, I hope this exploration has given you a new appreciation for the technology that surrounds us. A refrigerator isn't just a box that keeps things cold. It's a carefully designed system that manipulates the flow of energy, working against nature's tendency toward equilibrium, using cleverness and physics to create the coldness we rely on. Tomorrow, when you open your refrigerator to get milk for your coffee or vegetables for your dinner, take a moment to think about what's happening. Inside those walls, refrigerant is flowing. The compressor might be running, compressing vapor. Heat is being absorbed in the evaporator, transferred through the system, and released at the condenser. Insulation is resisting the inflow of warmth. And all of this is happening automatically, invisibly, reliably, keeping your food fresh. It's a small marvel, this refrigerator. Not flashy or glamorous, but essential and ingenious. And now you understand it a little better, the quiet complexity hidden behind that simple door. If you're still awake and you enjoyed this peaceful exploration of refrigeration, consider subscribing to the Sleep Wire channel for more gentle journeys through the technology around us. We'll continue exploring how everyday things work, uncovering the physics and engineering that make modern life possible, all presented in a calm, sleep-friendly way that helps you unwind and drift off. For now, though, rest well. Let your mind settle. Let your body relax. And perhaps as you sleep, dream of cool spaces and flowing refrigerant, of heat extracted and expelled, of the endless dance between warm and cold that happens in kitchens around the world. Good night and sleep well.